Okay, so today I'm going to talk about the SDN, the software defined network. So this is one of the most successful topics which revolutionized from the research paper to industry. So not many research paper become a reality, but SDN is the most successful research paper, and it is widely used over the industry, just out of the research paper. Okay, so we're going to talk about this. So what is the like a previous network look like? So you may heard of the Huawei come to the Huawei. Huawei try to contract with the Korean ISPs, Internet Service Provider. So we have about three ISPs, which is KT, SKT, and LG Telecom. So in their network, they have to periodically update the devices. So let's say maybe 10 years ago, we called, 3G is the best. Then we talked about 4G. Now in between 4G and 5G. Okay. And inside of 4G, we call the 4G first generation. Then after this 4G first generation is mature, then we move on to 4G second generation. We called LTE-A. Previously, we called the LTE. Then more version of it. Okay. So the version changes about 2-3 years. Version changes about 2-3 years. So now we talked about 5G and 5G, but maybe in 2-3 years, we're going to talk about 6G. Okay, so whenever this thing is changed, whenever new protocol comes to the market, they have to update the devices. So the Lucent technology, Lucent Tech, Alcatel, Lucent technology, and there's a Philips, Cisco, Foundry, and Samsung there, and Huawei there. Huawei is the most rapidly growing company in this business. Okay, so now the backbone of the LGT, about the I think about the half of the backbone of the LGT is Huawei device, because Huawei is not expecting make money, but thinking about the market first. So they come to market at the bargain price, and because after they're using it, they build up the trust, then they keep updating the new devices. Okay, so this is about $1 billion business, even in a small country like Korea. So whenever new thing is changed, we have to reinstall every hardware. We have to reinstall every software, which is too much money and too much waste. How can you solve this? That is SDN. How can you do? So make the hardware fastest enough and make a dummy devices. Why this is dummy devices advantage? Because chip, it does a very simple thing. And important things goes up to the main controller. And from here, everything is software. Then I can update while it is serviced. Okay, then I can replace my dummy devices easily. Not with the burden. I don't need to shut down the network. Just replace the dummy devices, and it is cheap. And main control, which is the key, and I can install and I can update over the air. That's the power of the software. Then this network industry become a software defined network. We call the software SDN. So let's talk about this today. So introduction, and I'm going to talk about what is SDN, and what is open for, and what is research problem in SDN. So long time ago, AT&T is the biggest ISP in US. Eyes on flexibility, eyes on cost saving with the new network design. So we all need it. They posted on the Wall Street Journal in 2004. So upgrade their internal network infrastructure, router and switches every 18 months to keep up with the current demands of network. So 18 months. Even you purchase the huge money, even you invest huge money, you have to periodically update it, which means the service providers, the who's using the service, has to pay more money, right? Then that costs $1 billion to upgrade. Cisco's top of the line switch cost about $72K per device. So every 1 mile, I have to install this switch. I have to install this switch. It doesn't make sense in the view of the business. Okay. Other high costs involve many manpower to upgrade the network. This is only the hardware devices. Then I have to upgrade, and I have to shut down, and I have to have an alternative. Okay. So AT&T was eyeing on SDN capable switches, and it is only $11K. How could it be much cheaper with the same functionality? Because all the complex algorithm is not there. It's a very dummy device. So in the business of 2007, network industry was strictly following the OSI layers. So there is an app that's using OS and specialized packet forward hardware, not an issue. Then in an app, so in the routing, in the app, there's a routing management, mobility management, and access control, and VPNs and everything. And in here, up to here is millions of lines of source code. Okay, so it's managed by the RFC, which is a protocol, and there is a specialized hardware which comes with 500 mega gates. You understand the gates, AND gate, OR gate. So we are talking about FPGA gate. So it comes with the 10 Gs of RAM, okay, which is huge in the view of 2007, okay, and it consumes a lot of power. Then many complex functions back into the infrastructure. So OSPF, we learn it, the BGP and multicast and differentiated services and traffic engineering and net firewalls, and all these things are working together. So we call this an industry with a mainframe mentality. So everything has to be done on one device. Whoever wants to business, they come to the mainframe and has to serve. Then in 2015, this mainframe mentality is broken. So OS is not just OS. It has to include the app, and sometimes they handle the hardware. So previously, it was a closed equipment, software bundled with the hardware, vendor-specific infrastructure, and overspecified because of the slow protocol standardization, and few people can innovate. Equipment vendor write the code, long delays to introduce new features. Okay, now operating network is expensive. More than half of the cost is the operating cost, and operator error causes most the outage. Someone typed the wrong information, then network doesn't work. So buggy software in the equipment costs huge money, and routers with the 20+ million lines of code and cascading failure and vulnerable issues. So this is the picture of the traditional network router. So router can be partitioned into control plane and data plane. Control plane and data plane. Okay, so router, so management and plane. Management plane is configuration. And control plane make a decision. Which path, which port, and which interface should I go out and should I take it? And data plane is just forwarding, just doing their job based on the table. Okay, traditional network router in summary. So the typical networking software comes with the two-part management plane, and comes with the management is up in by the software, and hardware comes with the control plane and data plane. So control plane is a brain and the decision maker, and data plane is do the work that we call the packet forwarder. It does nothing, but it just look at the table and do the work. Okay, so it could be much simple and it could be much smarter, which means I can focus on, if I can separate these two, I can focus on the speed, I can focus on the smart. Then all the algorithm comes in here, all the hardware improvement comes in data plane. Okay, so what if the network is dividable? Control plane and data plane. So if I have the switches with the dummy functionality, but it is very fast, and there is a logical and centralized control, and that is smart. Why does it need to be centralized? If the software comes in here, and here, and here, if the new features are coming in, I have to update every devices over the network. There are millions of the devices. And that can cause the problem because the hardware doesn't need to be one device. It could be multiple devices. And I have to update, and I have to write the code in a different way. So if I have one code which works for everybody, and they are just dummy, and they're just following the table. So this brain gives you the table. Just give a table to each other. Does nothing. They have no brain, but a fast hand. Okay. This is the imagination SDN concept. So I want to separate control and data plane. Why? This is the traditional network router. It comes with the this one router with the one package. I want to update some functionality on OSPF. What can I do? I have to update on-site and controlling it. Oh, update is successful. Then I move on to next spot, then controlling. I have a millions of spots to visit. Okay, let's separate those. Then I don't need to visit every time. There is just dummy devices. Just follow my table. Okay, that's the concept of SDN. SDN concept is basically separate the control and data plane. So SDN with the key abstraction. In the data plane, what they do is almost nothing but a fast hand. I do fast based on the table that I have. My brain gave me a table, then I just following it. And in the control plane, so we call the network operating system. And on top of it, there's a security function, there is a routing function, there is a traffic engineering, there's other applications via network virtualization. So everything working in one computer in here, then they are distributed. This forwarding switches are distributed. Okay, so let's say I come with the bright idea and I want to update my routing path. Then I can update in here. Then network OS will take handle. I only need to update the one line. I only need to handle one computer. Previously, I have to visit there, update, make sure it is working, then move on to the next. In here, just update it there. If there is an issue, I can fix it in one spot. Okay, so SDN basic concept is separate the control and data plane entities, and network intelligence and state are logically centralized. The underlying network infrastructure abstracted from the application, and execute or run control plane software on a general purpose hardware, which is our server. Then I can decouple from a specific network hardware. I don't need to buy an expensive vendor specific device. I don't need to buy a 50K Cisco. Oh, my computer just works. Okay. Then I can use the commodity servers and switches, which is much faster and much cheaper. Then I have to have a programmable data plane. Why? Because I have to have ability to read my table. That's the capability what I'm expecting. I don't need to make a decision, but I have to have ability to read my table. It can only maintain and control the program data plane, and it is controllable by the central entity. And the architecture to control not just network devices, but entire network. So entire network in one software, in one interface. Okay, that is the concept of the SDN. So in the real world, so SDN is so successful because Google chose this. So industry was skeptical whether the SDNs are possible. Does it really work? Google had a big issue. So high financial cost to managing their data centers, the CDNs. So if you think about CDN of the Google, if you think about YouTube servers around the Korea, around the China, and all over the place, there are tons of the CDN servers. And the hardware and software upgrade. So your YouTube and the CDN data centers are periodically updating over the provisioning, meaning fault tolerant, meaning something wrong. I have to keep maintain my services, right? And manage a large backup traffic, and time to manage individual switches matter, and a lot of manpower to manage the infrastructure. Long time ago, we called the network engineers. Everybody visit there and upgrade it and come back, make sure it is working properly. And delay caused by rebuilding connection after the link failure, and slow to rebuild the routing tables and after link failure. And it is difficult to predict what the new network may perform. And Google went ahead and implement SDN, built their hardware, and wrote their own software for their internal data centers. Surprised the industry when Google announced SDN was possible in the production in the real scale. Okay, so where they started? It started from this paper B4. So experience with the globally deployed software defined in WAN in ACM CCOM 2013. CCOM is the specialized interested group in communication. This is the best. This is the best space in the venue of the network. They may pick the 20 to 30 papers per year, and if you can write this is the best place what the human can write in the business of the network. Okay, I don't have a CCOM paper, but I wish I won't have. So origin of the SDN, the Martin Casado is the father of the SDN. He was a student at Stanford, and team proposed a clean state security architecture, insane, okay, which defines a centralized control of the security and generalized to all access policies. Okay, the idea of the software SDN originated from the Open Floor project in CCOM 2008. Okay, then Stanford published the Open Floor version 1 in 2009. In 2009, Martin Casado co-founds Nicara. And Open Networking Foundation is formed in 2011. In 2011, Open Networking Summit, many industry announced to incorporate with the Nicara, the startup just out of the lab. And VMware bought the Nicara at the 1.26 billion. Wow, right? The student become a billionaire with 6 years. You wrote the paper in the CCOM, then in 6 years, you become a billionaire. This is the business of the computer science, right? So lesson learned, imagination is the key, and unlock the power of the possibility. So this $1.2 billion is most of the cash. So when we talk about someone in M&A to the others, they are using the stocks, but this one is most of the cash, and he becomes an actual billionaire. Okay, so let's take a look at the this 2008 open floor. So what is open floor? So my job is separate the fast and dummy and smart, centralized and control one. Then I can distribute this fast and dummy devices all over the places, and I maintain one centralized device. Okay. So on top of it, an application can do their network or security or routing and all these things. All right. So inside of it, so open floor protocol, and there's a control plane, the minimum, and open floor and the actual hardware, which does the fast work. Okay. So an open floor allows the separation of the data plane and control plane, and it has a centralized control, and it is flow-based control, and take advantage of the routing tables in Ethernet switches and routers. SDN is not open floor, but SDN is a concept of physical separation of the network plane and data plane. And open floor is communication interface between control and data plane of the SDN protocol. So this open floor allow you to communicate between control plane and data plane. So open floor is a communication interface between control and data plane of the SDN architecture, and allows a direct access to and manipulate the forwarding table of the network devices, such as switches and routers and physical and virtual. Think of the protocol used in switching devices and control interfaces. So this is the SDN and the open floor in a nutshell, and everything is plotted in here. So open floor allows you to programmable meaning you can enable, innovate, and differentiate everything and accelerate new features. If there is a new feature, oh, I can apply my network. My network is actual size of the industry. Okay, and there is a centralized interface. Then simply simplify the provisioning. Then I don't need to visit every places. And if I update, the whole network is updated. And I can see the global view, meaning I can optimize the performance over the whole network. And abstraction is decoupling and hardware and software, meaning I can separate the hardware and I can separate my brain. Then physical and logical configuration different. So data plane and control plane is separated. How they communicate by open floor. So this is the concept of the SDN and open floor. So basic open floor, how does it work? So I have data plane simple devices which works with the table. Then there is a control plane, SDN controller, and they can learn it from back learning, routing all the algorithms in one server. The controller manages the traffic by manipulating flow table. So they only look at this flow table. Then I can properly update this flow table. That's it. So when the packet arrives, if it is matched to the flow table, oh, I do following action. If not, I just discard it. How simple it is. So if any enter is matches and performs the indicated actions and update the counters. If it doesn't match, the switch asks the controller by sending messages with the packet header, meaning, so if it is known, I can just keep doing. If it is not known, I'm asking my brain, what should I do with this packet? Okay, they're very simple and very flexible. Like you are hiring the interns for the restaurant. Okay, so if this is what you do, to clean the table and be nice to the customer. If you don't know, ask me. So I have one brain in the small store, then that brain works, and every hand and works as fast as it is. They don't need to think. Okay, you want to follow your orders. You want to follow your logics. Okay, so actual flow table looks like this. If the destination is this guy, I do action for port 1, meaning if the destination comes in this, I forward it to port 1, and I can keep increment my counter. If the destination IP is this guy, and forward to port 2 and increase my counter. Okay, so I can be this asterisk means anything. So if it says something on it, then I can do something. Okay, so open flow table and basic actions are to all interfaces except the incoming interfaces, and controllers encapsulate to send to the controller, and local is a send it to the local network stack, and table is perform actions in the next flow table, and import and send back to the input port, and normal is forwarding using traditional Ethernet. Flood is sent along the minimum spanning tree and accept the incoming interfaces. So flow table is very simple. It comes with only 7 instruction. Whenever there is coming in, and I can do this following, these 7 actions. Okay, so basic stats. So I can maintain my table. Per table, I have packet lookup, packet matches, and active entry. Per floor, so open floor is per flow control. So what can you do? If I receive the packet, I do something. If I receive byte, I do something. If the duration is too long, I can do something. Okay, so per table is a higher concept. Per flow, then, so more abstract and big, more detail. Okay, so provide a counter for incoming flows and packets, and information on counter can be retrieved to control plane, can be used to monitor the network traffic. Okay, so additional feature to rules and stat. So the OpenFlow 1.3 comes with the per flow meter band, which is threshold. Let me see the OpenFlow version today. I think I saw 1.7 OpenFlow version. Oh, it's a 1.6. It's the latest version. One second. Let me share with you. So 1.6. Okay, so after 2013, it's not that active, but we're still using this. And it has 1.6 version, OpenFlow network hypervisor. Roadmap. Oh, 2.0 is not coming. OpenFlow 2.0. Oh, there is a new 2.0 OpenFlow. Hypervisor. Could bring Cisco. Oh, so Cisco released the version OpenFlow version 2.0 in 2009. Okay, so 2.0 is available on the market. So we can see how they are evolved over time. The main concept, and there is more and more and more. The concepts are added. So whenever you release the new function, new business, you don't need to implement everything there. Just from there, as a version 1, then you can keep increment, keep improving. That's the power of software. You don't need to be perfect. Okay, so there is additional features to rules and stat, and these are the main features that are implemented in the OpenFloor in the earlier version. And switches that support OpenFloor, it comes with the Juniper series and NEC series, WiMAX, and most of the Cisco devices, most of the HP, most of Netgear, and PC Engines and Proton and Sienna, and many more support OpenFloor. So I tried to purchase the OpenFloor in Korea, but it's too expensive for me, for this school. But in the view of the industry, it is cheap. So I have one device which was cost about $500. If you want to test your OpenFloor, and if you want to implement the OpenFloor, you can check out the device from me, and I can let you use it. And I spent about 6 months only on OpenFloor. So right after graduating my master program, I worked in the company, and they were like implementing the OpenFloor concept. And then after spending 6 months there, and I changed my job. Okay, a long time ago, it wasn't working properly. So I did debugging and debugging. Okay, so OpenFloor switch software. So OpenFloor is the concept, and there is the backbone software. Then from there, everybody poke from there. So there is a Indigo. Indigo is open source implemented in Mac OS, and Link work on the Linux Solaris and everything. And Palm2, OpenFloor supported WRT. Do you know what the WRT is? No. So WRT is the FPGA closed the programming language. It is we don't using anymore, but a long time ago it is very friendly with the hardware. Therefore, it is much faster, and it works with the Atheros and the Broadcom. And 13 software switch works with the Ericsson devices, and OpenFloor virtual switch, and is popular. It's very popular and works on every devices in 2014. And this often virtual switch software comes with the it is based on the Kira concept, and can run on standalone and with the multiple physical servers. Do you understand the hypervisor concept? No? So let's say you just purchased new computers. So let's say it is Xeon. Let's say it is Xeon. It's a Xeon. Okay. Let's say you just purchased 4 computers, and you want it to work as a one. How can you do? So rather than it is individually working, it's better to perform as one, right? How can you do? Then we call the hypervisor. You install the hypervisor on top of these one, every devices. Then based on this one hypervisor, there's only hardware and hardware and hardware. Every instruction comes in here and make a decision. And this hypervisor make it possible, realize that even you have a multiple computers, it look like one. So Amazon AWS using a hypervisor. They have millions of servers in their backbone. And I'm only have one interface to controlling it, right? So that hypervisor allow you to access to the device by device level and make it works, make it look like they are seamless. Everything look like one. Okay, that's the concept of hypervisor. And the Gen server, Gen is the one of the hypervisor. So default switch in Gen server 6.0 and Gen cloud platform, and support the VirtualBox. So VirtualBox is the AWS kind of thing for the research. So in 2015, in 2016, there was a hypervisor, there's a gen, there's a VirtualBox, and many things. Now everybody using just AWS, right? So a long time ago, the neighbor has their own cloud, the KT has their own cloud, but everything is go out of business, and we are just using AWS and integrate into many cloud management using OpenStack and OpenQRM and OpenNebula, and distributed with the Ubuntu, Debian, and Linux and FreeBSDs. Okay, so the best place you can start is the Ubuntu. So controller plane. So now we talked about the virtual data plane, which works fast. Okay, now you have to think about your brain. The POX is a Python based. It is out of date, but it is still working. We tested with in the previous lectures, previous semester, previous batch of the CSC 310. We did with the 310 with the SDN and OpenFloor. This batch we are doing the SDR, right? The previous batch was doing SDN. So POX and Iris and Mole and Nox is all different software, all different languages, and friendly with the Python, Java, C, C+, and Python. Many of those. There are so many, but we are preferred to use the Python. And Nox is most stable version. And I believe we did every team was using a Nox. Okay, so back to the OpenFloor, back to the SDN and OpenFloor. The OpenFloor supports the different applications, something like routing, load balancing, and monitoring security, and everything that the router can do. And it is programmable and modify and interact with the network model and control plane. And I can have a global view because everybody is connected to me. And it is centralized per floor based control. So where's the new flow, I can make a different action. There's new flow, I can make a different action. Okay, and it is distributed system that creates a consistent and up-to-date network view in real time, and I can patch my new policies. I can patch my new security in real time. Then I'm much more stronger. Okay, I'm more like fortified by the anonymous attack. And the OpenFloor use an open protocol and gets data information from switch and give control directiveness to the two switches. And packet forwarding according to the instructions stored in the flow table and provide statistics on the network traffic to the controller, and hardware is just a dumb switches. Okay. So we talked about the network applications and program languages and language-based virtualization. And we talked about the control plane. So make decision and instruction. How can you update the routing table? Then your data plane on the southbound, we call the lower bound the southbound, upper bound the northbound. Okay, southbound interface is a firmware heading instructions from control plane and via flow table. So in the lowest level, they don't really care. They only care about flow table. What should I do if this happened? What should I do if this happened? They don't think. They just follow the instructions based on the flow table. So network hypervisor is virtualization is based on this network hypervisor in between control and data plane. So it hides the complexity. So, oh, there's something happened. We are doing because of this. We are doing because of there's policies behind. So your workers doesn't need to know. Just do. They don't need to think. Why is this happening? And what should I do the next step? Next step is different flow. Okay. If there's something happened, do this. If there's something happened, do this. They don't need to think about the after that. Okay. For flow. Okay, so network operator delegates control of the subset of the network and hardware, and multiple controller can talk to the same set of switches. So if I have one switches, I don't need to follow the one table, but I'm working on one table, and from time 1 to time T2, if the time has changed to time T2, I can just follow the table 2. Okay. Therefore, so table 1 is keep running. If the new is updating, then I can make a table 2. Then I'm waiting for the table 1 end. Then I can, the workers just take the table 2, just keep working. Okay. So therefore, I can update over the air without system failure. Okay. And it is the concept of the virtualized network model. So if I look at here, so you don't need to have one controller. I could have multiple controller. I can means I can. So if I am the like interns in the small restaurant, I can work in one store. Then if I move to the second store, I can work in different job, right? Also the controller, I can manage one store, then I can move to the second store, then I can run it again. Okay. So open floor may be managed by the multiple controller. So maybe 2 managers there. Then there's time series. It only takes one time at one. And at the same time, this open floor may serve, this open floor may serve as these 2. This controller may control everybody, and there is a secondary that control the subset of those. Okay. And it is very flexible with this. Many control scenario is possible. Network hypervisor is flow visor. So network hypervisor deployed by the Stanford, and software proxy between the forwarding and control plane, and allow resource to be sliced. Sliced is the main concept of the cloud service, meaning I have these resources. Okay, Xeon CPU core 40 CPU. I have RAM 128 gigabyte. The SSD is 10 terabyte as one device. Let's say one user is coming. Oh, I can slice this too and work on it. Oh, new users coming. I can slide this too. So one user does need to use from here to here. I can slice them with the virtualization. When the new user coming, oh, you can slice that portion, then working. Okay, so policy language specifies the slice resource limit and flow space and controller's location in terms of the IP and TCP. And flow visor enforces transparency and isolation between slice by inspecting, rewriting, and policing managed by the passing. Meaning, if I am the user in here, I cannot pass it. I cannot pass it. They are 2 different computers. Okay, I cannot access to it. I cannot. They are completely isolated and transparent. If you want to come to me, then you must pass through the controller, hypervisor controller. Then if you want to access to this guy, meaning you go to outside and runs on hypervisor, then you may go. But even you are in the same hardware, you cannot go. It is not permitted. So network hypervisor is slicing resources. So flow visor is assign hardware resource to slices. And topology is how they are connected. And in the physical port, and bandwidth is each slice can assign to the per port queue and fraction of the total bandwidth. Even your network is sliced, and the CPU is also sliced. And forwarding table, each slice has a finite quota of the forwarding users. Then if I have one device, then I could have I can work as multiple devices, right? Once I purchase the expensive device, I don't need to work as one device. Then it could serve as a switch 1, it can serve as a switch 2, it can serve as switch 3. So let's look at the northbound interface. Northbound interface is API to management plane and applications. It's an open issue as there is no standardized. So northbound is the how do you connect your apps to your brain. When the apps can be independently upgraded, right? Then how can you manage your network? How can you reflect it fast enough and effectively? This is kind of the open issue. So, and there's a language-based virtualization. So language meaning you may use the Python, you may use the C#, you may use the Java. So modality should be different based on your programmable languages. Okay, so even you are using different languages, then it should be virtualized. The functionality should be same. And program languages is vendor specifics a long time ago. Now program language interfaces to implement SDN. So even there is a multiple task of the single application then have to work with the others. Then how can you communicate with the others? And checking the conflict rules and provide a higher level of the programmable programming interfaces to avoid the low-level instructions and configurations. And on top of those, this is app level. So how you optimize your network using the big data app. Then how can you work with the NAS, the network as a service? And how can you work with the NOx controller? How can you differentiate? And how can you run the floodlight control? And how can you migrate? Migrate meaning I have one CDN in the Europe, I have one CDN in US, how they are synchronized properly. Then you may, if the EU's in UK server it goes down and I want to move everybody to the France server, then this has to be migrated. Then what is the best way to migrate it? And how can you back up your data properly and secure enough? And there's NetGraph, it shows the management plane, and OpenTCP is dynamically programmable TCP. And all of them employs the open floor to communicate with the switches. And the more application for the data center networking, and there is a Velo system and allow overriding layer 2 and layer 3 and cross-layer concept and live virtual machine migration within the across the data center networks, and provide a view and global cloud of the WAN, wireless, the wide area network, and provide network automation for LAN, local area network, and wide area network connectivity, and the provisioning. So provisioning is kind of the fault tolerant. If something goes wrong, what should I do? You should have a backup plan. Okay, even if some part of device is fault, so you should have a provisioning. You should keep maintaining your work. Okay, and there is a Mininet. Mininet is a Stanford invented this, and it is realistic virtual network and running real kernel and switches application code and on a single machine with a single command. And 2 batches ago, Mininet was the final project. So research problem, how can you make it scalable? Meaning, how can you expand to the global level from the lab size? And the control plane, the bottleneck single controller is not sufficient to manage a large scale network. And how many controllers are needed to support a large scale network? And when to scale down, meaning, so we don't using it, but Yonsei in right across the road using AWS as a scalable function. We have a Solar, which is large enough, but Yonsei has a Solar counterpart, but that's not strong enough. Long time ago, before the AWS era, let's say Y Solar. So students want to register their classes for the next semester. Y Solar traffic was nobody for a year. Then, right? This peak. So if you look at the over the year, from 1st January, the end of December, traffic, no traffic at all before the semester. No traffic at all before the semester. How can you design your server? Does your server is designed for this peak or this normal status? How can you handle this? So what happened? So long before the era, they set it around here. Okay. So they are available, accountable for 10,000 users are accessible to the server. Then let's keep working. And the registration open, everybody accessed, then server down. Only few who made a click earlier can register properly. Then goes back, comes back, and this is ridiculous. It doesn't work, meaning system failure, wrong design. What's the right way to do? How can you solve this? Let's think about it for 2 minutes. Do you understand the concept, right? So let's think about this. They solved using AWS. Let's talk about how. Okay, I'm going to ask the students. Maybe 손예은 and 이재원 and Ulbek. Maybe Minheng too. Okay, let's think about, you understand the problem. So main problem is I have Ysola, which is, you can say, registration system over the year. On March, traffic. On September, traffic. Rest of the year, there is almost no traffic, almost no traffic, almost no traffic. What is right way to design the system? Is it 1, 10,000 users, or 2 is 100,000 users? Ready? 예은?
Sorry, I have no idea.
Okay, you understand the problem, right?
Yeah.
Okay. Who wants to try? Ulbek?
So,
Go ahead.
So how about like so way before AWS, there was still an SDN, right? So what I'm saying is that let's say we have multiple computers, and each computer is responsible for their own server or a job, but like there's really low chance that all of those computers will be on high load on the same day. So what I'm saying is that a computer who's responsible for Yancey's server on this day, when the traffic increases, it may utilize the hardware of other idle computers.
Okay, so Janari is saying, I have multiple computers, computer 1, computer 2, computer 3, and computer 4.
So there's
and
like a
registration, and
like
there's different
hardware
job
controller on top of them all, like you said before.
So if this network is virtualized, this issue is not happening. So good point. So Janara is saying if it is virtualized, so this program registration 1, slice open here when it is required. Then after this is done, then I can slice to this one, registration, right? But this require the virtualization and slice concept. This is the concept of cloud. Good point. But at that time it wasn't possible. So system was just go down. And whenever this is expected, like the last day of the February, then maybe install a new computer and moving to there. So previously only small computer was assigned to that. On that day, you are migrating to the big server, then you're migrating back. This was the popular concept. So let's say you have 10 computers, 10 mid-sized computer as one supercomputer in your like Yon says data centers. So there is a small computers who usually handles the registration and different services 1, different service 2, service 10, service 10. Then the mainframe will stay vacant and do their job. Then if this is replaced, if this is expected, this mainframe move on to medium server and this registration move on to mainframe. The migration concept. The migration concept. Meaning that your server was work fine, then you have to move. Because I only have one resources. I only have one strong resources. Then this one is move on. This is done by the hand, then it's done by the human. Okay. Of course, it is not efficient. And how after the AWS, after Yonsei choose the AWS, how can they do this efficiently? Why do we have no registration, like chaos is not happening? So like when I was a student, we were very popular to writing a macro. Macro is accessing to the keep clicking on my registration to enter the class that I wanted. So in SUNY Korea, you may be not imagine that, but if you think about, if you have 500 students are competing for the one popular 50 quota class. Okay, let's say this is very popular, EGA. Everybody just dive into this. Okay, then you have to go to top A and top B's classes. Okay, so there is always popular classes. Everybody wants to join. Okay, then you can have a macro, all these things. So how they solve this? How the human can solve this? Why is it not going to? Yeah. Okay. So how can we do this? It's basically slice. Because of network hypervisor, AWS sees as a multiple computers as a one. So you can say network admin, tune the price level. So over the air, I'm paying the minimum. If you're expecting this, oh, I'm choosing this one to this level. I'm changing my control knob, meaning I'm paying more for that time. So expecting more traffic. Then AWS allows more computers for that service. Then everything works smoothly. I don't need to migrate. I don't need to buy a new hardware. I don't need to do anything, but the AWS will handle by controlling knob with the hypervisor. Okay. Go back to the point. Okay. So scale down. I don't need to purchase the expensive hardware. I don't need to expect this one all over the year. Right? Just only 2 events a year, 2 days of event here. Then I can scale down easily. When this event is done, then I can roll back to the much cheaper price level. Okay. So multiple controller. So each controller, thank you, Janar. 4. So each controller is responsible to a subset of the network and concerned with the synchronization and communication between controller and how to slice the resources among the controller. So they are written in the policy and written by the network administration. So latency between controller and switches. So if the latency is high, I don't need to. So I'm keep using the latest one. So latency between controller and switch is very small. If the new traffic comes, then I can ask. If not, I'm just doing my job. If the new job is coming, I'm asking and I'm keep doing it. So because I have a multiple thread, I open the one thread and asking and waiting for the decision, but the other interface is still working on the network port interfaces. But if your waiting is too long, then I should do something. Or if I have a multiple of stock point, then your network goes down, right? How can you make it fast? How can you make a faster decision? So is it better to have a less accurate decision first, then make it work? Or does it need to be precise action, precise decision, then move on? What can you do? So basic concept is if it's related to security, I have to make a precise decision. If it is a policy decision, how fast can you make it? Then I can make a first decision, make a quick decision first, then I can think of again in a backend. Okay. And how can you slice your resources? Meaning now we understand the slice concept and slicing resources, CPU and bandwidth, and how to allocate resources to different controller and users, and formulate an fairness problem, and using SDN to achieve more green data center networks. And there's no substantial work in this area. And green work, maybe you saw some articles that the Microsoft put the CDN onto the ocean shore. All right, and we're going to talk about it in the next class. And maybe if I can share with you. MS underwater CDN. So Microsoft is putting the servers underwater. Why is it working? Why is it better than the just normal servers?
I think they said that. So after they after it spent some time there, they said that in the ocean there's less noise.
Okay, so if you
plus cooling.
Yes, cooling. Okay, if you think about Google CDN, where's the Google CDN is placed? Do you know? It's always near the water. Why? You have to cool the server. And the two options, I can put it to the near to city, which means it is less latency because there are many users, but it's noisy and expensive. But if I put in the rural area, there's nobody, I can make it cooler faster, but I'm creating more latency because there's no people living around there. The right choice is near the water, meaning near the ocean. Why? Most of the human population lives along the water, along the ocean. Putting on the shore, then I can solve the latency issue because it is very close to the human population, and it cools automatically. Okay, so do you know how many people started this the underwater project, the submarine? Only 5 of them. 5, the Microsoft Research started this, and now it is whole business. Only 5 of them. You don't need to have a huge team to be successful in the business. Okay, the right team just work. Okay, so in a one container, there's about 800 to 900 servers inside of it. And the inside of it look like this, all their servers. Okay, because there is no human, less failure. That's what they say. All right, go back to the slide. Okay, so using CDNs to achieve more green DCN, data center network. What we saw, so no substantial work in 2015. So ICC and Globecom was published in the subject. And how can you do turn it on and off? If it is not working, should we just turn it off and just working the minimum? How can you do? It's just everything goes, the software is better. We don't know yet. Okay, so there is a concept of the mini net and OpenFlow we talked about, and there's net FPGA. There's no green center yet. Okay, so in Songdo, there are many data centers. Do you know why? Songdo data center. The IBM data center is here. Kyobo data center is here. And IBK data center is here in Songdo. Do you know why? No?
Because it's always cold and windy.
Okay, good point. And at the same time, about 5-10 years ago, Songdo was so cheap and close to the Seoul. And it is always windy, like you say. And they started building a data center. And this, since it is IFEG, the cost of electronics is cheaper too. Okay, so it's a business problem. So business choice. So there is many references I put in here. So research paper, some research theme in an SDN. If you think about the research provisioning, how can you keep working? Then there is the work in there. You can take a look, and traffic steering and ad hoc topology and routing services and revenue models and middle boxes and other issues are all in here. And the conference called NFB and SDN. NFB-SDN is the best place you can publish your work in here. Network functionality virtualization and software defined network. Okay. So SDN data center is there's no clear definition. Everyone has their own definition. So buzzword about from the storage related to the industry. Everyone claims they have SDN data center product. So my guess is combination of the virtual machine and SDN is the concept of the SDN in the industry, and server storage and network virtualization and network plane, management plane, and global view. If they have global view and they claim, oh, we have SDN. So what's the academic work? So we just found out the concept of the SDN centers. Okay, so what is right SDN? The SDN CDN. So we just open the SDN CDN concept. Then if you have idea, then you can contribute to the industry. So now Google and AWS is a leader in here. So they are very fast. If the industry comes to the market, the academic usually leaves because the industry the speed of work is much faster with industry. Okay, so conclusion of the SDN. So key ideas of the SDN is dynamic programmability in forwarding packets and decouples a control and data plane, and global view network by the logical centralization in control plane, and application can be implemented on top of control plane. And CDN is concept to manage network that leverage the open flow protocol. Okay, and here is the references that I used for this lectures, and you can take a look. It's all open text. All right, any question about the SDN today? No. Okay, thanks for coming today, and I'm going to distribute the midterm score on the next week face-to-face offline class. All right. All right. Any question?
Professor, are you in the campus on Thursday? Tomorrow?
Thursday, yeah. I'm in my office today, and I'll be in my office tomorrow too.
Okay, thank you.
All right. Anything? All right. Thank you guys, and see you on Monday. All right. Good luck on your final project, and spend your time. Thank you.